All right, let's go and review some formulas that we've been using recently. There are 5 of them. Let's see, without looking at, say, index cards, textbooks, bulletin boards, let's see how many of these 5 formulas we can remember. And we'll start with Kendall. Kendall, give me any of the 5 formulas you can remember.
All right, so we have A equals B sub F minus B sub I over T.
All right. Audrey, give me another you remember.
BF squared equals BI squared plus 2AD.
Very good. All right, Michael, another that you remember.
D equals V sub IT plus 1/2 AD squared.
There we go. So one of them has a 2, one of them has the half, and the half has the square in it. Another that you remember, Kendall.
B sub AV equals 1/2 plus, no, times B sub I plus B sub F.
All right, and then the only one that's not up here yet, Audrey.
B sub AD equals D sub T.
There we go. Where class, the V's all stand for velocity, whether it's final, initial, or average. The D stands for displacement. The T is time. The A is acceleration. Time will be measured in seconds. Velocity in meters per second. Displacement in meters, and acceleration meters per second squared. Now, all of the motion we've dealt with so far has been, to some extent, horizontal or along the ground, this way. But you, of course, can have, as I almost witnessed, tragedy as I came into my classroom moments ago, Michael standing at the window contemplating life. I'm like, there's other girls out there, Michael, don't jump. I didn't actually say all that. I was like, don't jump. And he wasn't actually planning to jump. It's just beautiful weather outside, which in Georgia is not that common. And, and so anyway, had he jumped, he would have gone down. Why would he have gone down? Because gravity pulls him down, doesn't it? And Michael would have had no way of slowing himself or stopping himself. He just, down he goes. We call this free fall. That's the next term in your notes. Free fall. Now, it's kind of a self-explanatory term, but I'm going to give you a definition anyway for free fall. It is the downward vertical motion of an object. Free fall is the downward vertical motion of an object. Slightly redundant in downward and vertical, but not entirely so. Downward vertical motion of an object caused by gravity. Downward vertical motion of an object caused by gravity. Now, we understand this. If Michael, instead of jumping to his doom, decided to, I don't know, write a note to the neighbor, mow your lawn. And I actually don't know if the neighbor needs to mow his lawn or not. He does. He doesn't. He's good. Okay. Thank you for mowing your lawn. And we're to drop the paper out the window, right? Paper crashes down, right?
Yes.
Probably not. Probably it sort of flutters. Or for instance, Michael leans over the edge of the window and sees fair maiden below and writes, "I'm sorry," which is usually a good thing to say to a girl, and drops it over the edge, and it floats down. And so she's like, he sends me no, he sends me no. And then gets tripped up and falls down on her face, and then she's really mad at him. And even his note of "I'm sorry" just caused more problems, which just goes to show guys can't win, okay? I'm just kidding. Next time, crumple the paper up and drop it. Then it just goes down, right? Now, why? Why does paper just go down if you crumple it, but if you just toss the sheet of paper, it sort of does weirdness? Why? Air resistance, right? Same amount of mass, correct? Same weight, if you will, of the paper, but the surface area of the paper, the ratio of weight to surface area, or surface area to weight, I should say, is so much greater, it doesn't descend the same way. It descends much more slowly. For our purposes, though, trying to figure the ratio of mass to surface area and account for all of the variables that go into air resistance, that's just a pain. And so what scientists have done, scientists do, except for those who it really, really does matter a whole lot, is we say, well, let's just ignore air resistance, because most of the objects we will deal with would be like Michael, who air resistance just doesn't have a huge effect on. It's just, right? Most things, the air resistance effect is negligible. So for our purposes, make this note, we are going to ignore air resistance in our problem. We're going to, I guess, assume a vacuum. Now again, you're not going to extrapolate this too far. Well, he jumps and he's in a vacuum, so he hits the ground and goes splat. But he's only 2 stories up, so he doesn't splat too hard, but it's a vacuum, so there's no air to breathe, so he dies anyway of suffocation. Okay. We're not going to go into that, okay? We're ignoring the air resistance, as if there were a vacuum present. For instance, that same sheet of paper in a vacuum really would just fall. There would be nothing to hold it up. There would be nothing to cause its flight to be different. So a rock and a piece of paper fall at different rates in air, but in a vacuum they would fall the same. The book uses the example of taking a tube from which you can pump air and allowing a feather and a ball to drop. They drop at the same rate. With air in the tube, they fall at different rates. Okay? But for our purposes, we're just ignoring air resistance. And if we ignore air resistance, all objects will fall at the same rate. By same rate, we mean the same rate of acceleration. If Michael jumped out the window, now his descent would not take long, right? But if Michael jumped out I'm not advocating, by the way, that Michael jump out the window. We're not recommending people jump out windows, okay? But if Michael jumped out the window, he would actually fall faster and faster and faster before he hit the ground. It just wouldn't take very long. But, as I think I mentioned, right, once before, the rather sobering sight of people jumping out the windows of the trade towers, they did get faster and faster and faster until eventually they died as they hit the ground, or perhaps we said possibly died in the air of a heart attack, anticipating the adrenaline rush may have been too great for them. But all objects in free fall will accelerate, will get faster and faster and faster and faster as they fall. And this acceleration for an object in free fall is simply g, which we're going to say is 9.80 meters per second squared. Now again, that's an approximated value. It varies depending on where you are on the Earth. It even varies depending on your altitude, right? Higher altitudes will have a lower acceleration due to gravity, but it would be like 9.78 or 9.77 instead of 9.80. So it doesn't make that big of a difference. We're just going to make our lives easier and go with that value. But 9.80 meters per second squared, that's what we're going to use in our free fall problems. So every one of these problems where you see an A, if the object is in free fall, we already know the A. It won't come out and tell us the A because we'll already know it. So you know how we've made lists of numbers and it says something about starting from rest, and we say, ooh, wow, we know from this that the initial velocity is 0. There's a hurricane about 200 miles south of us, and so the outer fringes are causing air currents to speed up, and we're getting quite the breeze out the window right now. It would feel great if I could feel it. All right, I'm sure if I were out there, it would feel great. Tomorrow for PE, by the way, we're supposed to have 15 to 20 mile an hour winds for playing softball. No rain though. So yes, it's going to be a windy day. I just hope the rain is not blowing at me as I'm pitching and getting dust in my eyes so it's hard to see. So, we're safety goggles from the science lab. That won't look weird. All right. Anyway, what I really hope for is a cross breeze, right? That blows the ball right at the batter. So I toss the ball way outside, it blows it across the plate. That'd be great. Anyway, back to physics. Where was it? Yeah. So remember we said if something starts from rest, we're like, oh, the initial velocity is 0. Or if something comes to a stop, we're like, oh, okay, that means final velocity is 0. Well, now if the problem implies vertical motion, we know the acceleration is the 9.80. It won't tell us that acceleration. Does that make sense? All right. Now, a couple of other thoughts, though. So anything that's in vertical motion has that g, including something going up. Now you say something going up. Does something going up accelerate? No. What happens if I throw a ball up into the air? It slows down until it reaches a point at which it stops, right? Why does it stop? Because it's being decelerated, but it's still gravity pulling on it. So if I intend to throw something upward, gravity's working in an opposite direction. How do I show opposite direction in physics? Negative sign. So for something going up, if I intend it to go up, what would the acceleration be? Meters per second squared. And when something's going downward, for instance, if Michael's like, There's my sister. Drops water balloon on her head just because, I don't know, he seems like that kind of guy. I would totally do that too. If I had a water balloon and my sister were here and she were under the window. My other sister, don't worry, Melissa. All right. My little sister not subscribed to my YouTube channel. Just in case Melissa randomly picked this video to watch, we're talking about Michelle. Shout out to Michelle. Love Michelle. All right. Love to drop water balloons. Anyway, getting myself in trouble here. Guess I'm not going home for Christmas. All right. Something goes down. Then gravity class is the positive 9.80 meters per second squared. Right? Again, really it's kind of dependent on the intention. Oh, here's another thought, right? Well, what if you throw something downward and it ricochets and comes back upward? Gravity's still negative, right? So anyway, gravity, we're going with the 9.8. We'll account for the positive, negative as we take it problem by problem. But as a general rule, something going up, we'll assume the gravity's working against it, so it's negative. Something going down, gravity's positive, it's accelerating it. Now, realistically though, right, that piece of paper, there really is air resistance. And in many cases, we're really, really thankful for air resistance, right? We said airplane flight wouldn't be possible in a vacuum. Jumping out of a plane with a parachute wouldn't be possible without air resistance, right? So we said that Michael, as he jumps out of the window, gets faster and faster and faster and faster. We said the people who jumped out of the trade towers got faster and faster and faster and faster. There is a point at which, though, air resistance will build and build and build to where at some point you'll stop speeding up. That's the idea of the parachute. You jump out of the plane. Now this is how I heard it's done. I've never done it. I never will. I hope, I pray, I never will have to, because I have no intention of jumping out of a plane on my own. Who said they wanted to jump out of a plane? Okay, you two, and you're like me, terra firma, I like that. Feet firmly on terra, okay? But you do want to jump out of a plane. I think the way it works is you don't do this without actually consulting an expert. This is not advice on how to jump out of a plane. And comments are turned off, so you can't tell me I'm wrong, because I probably am. But I think you jump out of the plane and you have to wait like 5 or 10 seconds before you pull the cord and the parachute opens. I think that's how it works. Now, part of the reason is you want to get up enough speed the parachute will fully open. Also, you want to make sure you're clear of the plane. So that way the parachute doesn't get sucked into the engines or chopped up by propellers if it's a prop plane. Okay, but pull the cord, parachute opens, and what happens is it grabs a whole lot of air resistance for you because it added very little weight, but it gave you a great deal of surface area. And what it does is it slows you down, right? Theoretically, if you started with the parachute open somehow as you jumped out of the plane, you'd speed up, speed up, speed up, speed up, and you'd hit a point about 25 miles an hour or so at which you just stay that speed as you went down. So you continue dropping. I mean, 25 miles an hour is a pretty good pace, but at least it's not crash to your death pace, right? Okay, and as you descend, of course, the air gets denser, so it slows you down even a little bit more as you get closer and closer to Earth. But that's the basic idea. We call this maximum velocity terminal velocity. Terminal velocity is the maximum velocity an object can reach, a freely falling object can reach, rather, because of air resistance. So the book uses the idea of even a coin. You drop a coin out of a window. Well, it'll tend to flip end over end, which creates more air resistance, even artificially. It's got a wide surface to it. A coin doesn't continue to speed up and speed up and speed up the whole way down. It'll hit a point where it just stays going really fast. Okay? Aerodynamic objects, though, won't necessarily hit this terminal velocity, right? A bullet that is fired downward, or a bullet even that's fired upward and then comes back down, right, will come down with a great rate of speed because very little air resistance for something like a bullet. It's designed to be aerodynamic. The piece of paper hits terminal velocity almost instantly, and hence you see it float. If we have time at the end of the hour, I don't think we will because I have to release you early for pizza day, but maybe tomorrow. You see those little toy parachute people? Ever play with a toy parachute? My little kids enjoyed playing with toy parachute people. There was a weekend I had to be here getting some work done, so I gave them toy parachute people, and they went and played on over the stairwell. Okay, so you already know it would be boring for you anyway, so we won't bother. But dropping the toy parachute people, and they fall for maybe half a second. You see them falling, and then it's just sort of glide the rest of the way. Why? They have almost very little mass in the first place, a great deal of surface area, so they just kind of float down at a steady rate, right? They hit terminal velocity quickly. Their maximum velocity, and every object has a different terminal velocity. You see on the textbook there on page 92, two meanings of terminal velocity. the one guy has already reached terminal velocity, and the other guy will hit terminal velocity. Probably should open the parachute. But anyway, let's go and take a look at page 90 in your textbooks, and look at example 6.9. Audrey, read that for us if you would.
A boy on a bridge dropped a rock into a river flowing below, ignoring air resistance if the rock fell for 3 seconds before hitting the water. What was its velocity the instant before impact?
All right, so look at all the things we know. It says he dropped a rock. He didn't throw a rock. He didn't toss a rock up. He dropped a rock, which implies the initial velocity of the rock class was 0. And then it begins to fall. What causes the rock to fall? Gravity. So we here know the initial velocity is 0. We know the acceleration is the 9.80. By the way, positive or negative? Positive. He intends the rock to go down. Positive 9.80 meters per second squared. And it fell for 3 seconds. That's the only number in the entire problem, but class, that's the time. Time is 3 seconds. It's a ghost, Michael. Don't worry about it. And it asks, what was the velocity the instant before it hit the water? So we're looking for the final velocity, right? So we take the acceleration equation and we manipulate it for the v sub f. So we multiply the t, we add the vi is 0 anyway. So we just multiply the t. And that's what they did. They multiplied 3 times 9.8 to get 29.4 meters per second. Questions on that? Notice it says ignoring air resistance. It won't necessarily say that every time, but we will assume we're ignoring it. And frankly, is a rock really going to be affected much by air resistance? No. All right, example 6.10. Read that for us, Kendall.
Suppose the boy...
The ghost just shut the door for us.
Suppose the boy threw a rock down at 5.00 meters per second into a river instead of just letting it drop. If the velocity immediately before impact is 29.8 meters per second, find the time required for the fall. Assume.
All right, so here, instead of dropping it, it says he threw it down. So class, what's the initial velocity?
5 meters per second.
5 meters per second. And it tells us that right before it hit the ground or hit the water, into the river, okay, right before it hits the river, it's going how fast?
29.8 meters per second.
Okay, and we know because once he throws it, it doesn't go at a constant 5, it speeds up because of gravity, which accelerates it at?
9.80
Meters per second.
And so the question is, how much time did it take for the fall? Well, same equation again, this time just alternate. And that's what they did. They took the final minus the initial, divided out the acceleration. You see that there, the time 2.53 seconds. Questions on that? Pretty easy. No new equations. Same 5 formulas for you to be successful in this chapter. It's just the A becomes G, 9.80. If they write it with the letter G, you don't have to write it with the G. Just know what to plug in for the A. Make sense? Not wrong to write it with the G, just I'm lazy. Example 6.11. Read that one for us. Oh, there's a lot to this one. Michael.
An arrow is shot upward with a velocity of 1 meter per second.
What?
100.
Oh, I thought it 1 meter per second. That's slow. Okay, gotcha. Sorry.
How high will it rise from its point of release? How much time does the ascent require? How much time will elapse between its release and its return to its starting point? What is the arrow's speed when it reaches its original position? What is the arrow's velocity when it returns to the starting point?
All right, so a lot going on here. Again, 100 meters per second. I mean, that arrow would fly from the length of the PE field in a second. That seems a little fast to me. Maybe not. I'm not a bow hunter. But regardless, let's just say this is Robin Hood, okay? And he can shoot an arrow 100 meters per second, okay? Don't argue with me. That's the initial velocity, 100 meters per second. But he shoots it straight up. Now think about it. If he shoots it straight up, what's going to happen to the arrow? Before it comes down, what's going to happen? Just as soon as it leaves the bow, what's going to happen? It's going to slow down. Why? Because gravity's pulling it down, so gravity's decelerating at...
Negative 1.8 meters per second.
All right, and it's going to slow down, slow down, slow down, slow down, slow down until eventually it stops. Now, just for a split second, right? And then it'll begin coming back down again. Probably because of the fins on the back, it'll reverse course, right? But it'll flip in the air at some point. But it'll stop and it'll come back down, right? At that moment, that's going to be my final velocity. Not of the whole trip, but I'm just going to say for the trip going upward, okay? So I'm going to look at this entire launch of arrow shoots straight up, arrow comes straight down. Now again, let's not account for the rotation of the earth, wind currents, and air resistance here, okay? It goes up, straight up, would come straight back down. I realize that, which hopefully takes one step to the side, right? And it's fine. But anyway, we're straight up, straight down. Okay, so straight up, 100 meters per second, decelerates till it hits 0. And the question it says is how high will it rise? Again, we're only looking at up, but what's the displacement? Well, we can't use the acceleration equation for this. We've got to use which memorized formula will we use? VIA, VF, and D.
VF squared.
Good. The VF squared equals, say it with me, class, V sub I squared plus 2AD. Solving for the D, right? So we're going to take the V sub F squared minus the V sub I squared all over 2A. But the V sub F is 0. So we just take the 100, square it, and apply a negative. Divide it, negative 20, or negative 100,000. Right? Then divide by 2 and divide by negative 9.8. Or you can say, hey, this negative is going to cancel with that negative. I ain't going to plug in any negatives because I know it's going to come out positive. What do we get for the displacement?
510.204.
All right, so approximately, is it 360? Yeah, 510 meters. That's pretty high. I mean, that's a 17, 18, 19 story building. That's, you know, the government center downtown. So that's pretty high to shoot an arrow. All right, that's the first part, letter A. Letter B, how much time will the ascent require? Well, again, let's see if we can avoid using displacement. What equation would I use that uses just the other variables? Ooh, this is why I gotta have it memorized so we know what to pick from.
A equals VF minus VI over T.
Yeah, the acceleration equation, right? Put alternate to get T equals VF minus VI over A. But again, VF is 0, so it's really just 100 over negative, excuse me, 100 over negative 9.8. Again, cancel the negatives in your mind. Do 100 divided by 9.8. How much time does it take to go up?
10.2.
10.2
0
blah 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 seconds. So round it off 10.2 seconds. You know, I should have had, go ahead and store this in the memory of your calculator. I think I should have had you store the last one, but we'll see. Letter C. How much time will elapse between its release and its return to its starting point? Again, this is ignoring windage, ignoring rotation of the earth and how that might affect things. It's just straight up, comes straight back down again, okay? And so think about it. Once it reaches the high point, it now has to make a trip back downward, correct? How fast is it going at the start of the trip down? 0. It stopped, remember, just ever so briefly, but it stopped. So the initial velocity is 0. What is going to be the acceleration as it comes down?
9.8.
This time it's going to be a positive 9.80 meters per second squared. How far does it have to fall? The number I forgot to tell you to put in your calculator. The 510.20 blah, blah, blah meters is how far it has to fall. So how much time will it take to fall? Well, what equation has these variables in it?
T equals VI T plus 1/2 AT squared.
And I told you, I hate using this to solve for T. But since the V sub I is 0, what's going to happen right here?
0.
It's going to cancel. So if I multiply by 2, divide by A, and take the square root, we could double, just use this, it's an approximate, I know, so our answer's not going to be perfect, but take the 510.20, double it, and divide by 9.8, and then take the square root. How much time to come back down? Yeah, the same, virtually. Now, it's not perfectly the same because we used an approximate, but it's really close, right? The same 10.204 seconds. Question, if we wanted to find the velocity at which it strikes Earth, well, the VF became the VI, the A is the same, the D is the same, the T is the same. What do you suppose will happen with the V sub F? It'd be the same with the V sub I, but it's coming down the opposite direction. So, negative 100 meters per second if we were to take the time to calculate. So here's the thought. Again, not perfectly accurate, but a bullet is very minimally affected by air resistance, right? What goes up must come down somewhere. And however fast it leaves the gun, if it were in a vacuum, is how fast it would come back down. Think about that. Blasting through people's roofs. My parents had a bullet go through their garage door at a downward angle like this. Someone apparently somewhere in the general vicinity of where they live had fired a gun up in the air and the bullet came down through the garage door. Steel garage door. But it's a bullet. Bullets can go through the steel, right? And so that's why we exercise caution. We don't randomly fire a gun. What was the, don't put your finger on a trigger unless you intend to kill something? Or target practice, right? So anyway, some gun safety advice there. But anyway, how do we get off on that? We were on letter C, how much time? Oh, notice it says how much time will elapse between the release and the return to the starting point. So remember, it took 10.2 seconds to go up. It takes another 10.2 seconds to go down. So how much total time will it take? Well, what's the easy way to do that? Instead of going through all that math like we did, just double the memory value. So what's the total time in air class? 20.4 seconds. Shoots the arrow. Shoo! 20.4 seconds between fire and comes right back down. And hopefully, like I say, he stepped aside, whoever shot it. The next question says, what is the arrow's speed when it returns to its original position? Its speed is the same, 100 meters per second. But its velocity is negative 100 meters per second. Remember, the speed doesn't account for direction because speed is a scalar, where velocity is a vector. Questions on that? All right. Turn to page 93. And look at problems 13 and 14. Do you see how they look like they've got a lot in common there? The difference is, Kendall, number 13 asks for
velocity.
And problem number 14 asks for
Distance.
distance or displacement, right? So let's make a little chart for a falling object. Let's make a little chart. And we'll do 13 and 14 kind of at the same time. So time, velocity, and displacement. Now technically we're going to say final velocity. And so an object is dropped or released and it begins to fall. And it says after half a second, after 1 second, 2 seconds, 5 seconds, and 12 seconds. How fast is the falling object traveling and what is its displacement? For a falling object, again, we're going to assume the initial velocity is 0 and we're going to assume the acceleration class is 9.80 meters per second squared. All right, so let's start by just finding the final velocity. Let's not worry about the distance column yet or displacement column. Let's just look here. Which equation relates these variables? The acceleration equation. We want to get the v sub f by itself. So if a equals v sub f minus v sub I over t, and v sub I is 0 anyway, then the v sub f equals at. So all we have to do is take 9.80 times a half. How fast is an object going? For instance, if Michael only takes half a second to fall, how fast was he going? 4.9 meters per second? No, that's not too terribly fast. All right, what about after 1 second? That should be easy. 9.8 meters per second. That's sprinting speed. Okay, so let's imagine sprinting full speed into a brick wall or into the ground. Okay, that's how it would feel to Michael. If you jogged into the ground, that's how the half a second fall would feel. What about 2 seconds of falling?
19.6.
So we'll round to approximately 20 meters per second. It's 45 miles an hour. Straight into the ground. All right, how about 5 seconds?
49.
If an object manages to fall for a full 5 seconds when it strikes Earth, this again, ignoring air resistance, 49 meters per second, over 100 miles an hour. And then if an object managed to fall for 12 seconds, how fast would it be going when it finally hits?
117.6.
How much?
117.
117.6, so we'll round to 120 meters per second. Just insanely fast. Now, the next question, how far would the object fall? So now, let's say we didn't want to use the v sub f. What equation would relate these variables?
D over T. Oh, wait.
That'd be average velocity is d over t.
D equals V I T 1/2 AT
Good. D equals v sub I t plus 1/2 at squared, which is, an annoying equation, admittedly, but because the v sub I is 0, it's really 1/2 at squared. So we're going to take half the a. Well, what is 1/2 a? What's half of 4.8, or 9 point, what is half of 9.8? 4.9. All right, so we're going to take 4.9 times the time squared. So square the 0.5, multiply by 4.9. What do we get?
1.225.
1.225 or 1.2 meters. Sorry, Michael, it's further than a 1.2 meter drop out the window. What about 1 second? Well, that's easy. Square the 1 is 1 times 4.9. 4.9 meters. Now, Michael, that's presumably about the height to the window. So if you had jumped, you'd have fallen about this distance, so you would have taken about 1 second, and you would have been going full sprint speed into the ground. It would have hurt. Killed you, probably not, but hurt, yes. Okay? Which is why you wanted to take sheets and make a rope so you would get out, instead of just taking the stairs later. All right. Square the 2 times the half a.
19.6.
Okay, or about 20 point, now notice this is meters. So 20 meters per second, and you've traveled 20 meters. Again, you started at rest. So how about 5 seconds? How far would an object fall in 5 seconds?
About 120 meters.
120 meters? Wow. 40 stories? Maybe World Trade Towers height for some of them. Some of the floors higher than that. I think it was like 80 something floors in those buildings. That's only about 40 or so floors. So what about 12 seconds? For instance, you don't count very well as you jump out of the airplane. Now, they say count to 10, I think, is what I've heard. Probably because you're, just to give you at least some gap there. But let's suppose you're like 1, 2, 3. Okay, suppose you're counting slow and you count to 10, but it takes you 12 seconds to get there. How far will you have plunged?
706 meters.
706?
Wow.
So rounded 710 meters, which you're still not hitting the ground right then, but you're going very, very quickly, very fast. Long parachute. I can't even imagine. See, here's the thing. I can't imagine flying over 100 miles an hour, hurtling toward the ground. So, and yet that's only 5 seconds. That's only waiting 5 seconds. I wouldn't make it to 10 seconds pulling the cord. I wouldn't make it seeing the open chasm before me, probably. But anyway, more power to those of you who enjoy the thrill of 100 mile an hour drop toward the earth as you wait to pull your cord. Questions on this? All right. We will have to pick up with more of that in our next lesson because I have to let the seniors go early. Wait. At 45. I got time for one more problem. Number 15. Go ahead and read that if you would. Audrey.
Someone thinks he can shoot an arrow as high as the Willis Tower in Chicago, 443 meters high. A, at what velocity would the arrow have to be released at ground level? B, how long would the ascent take?
All right, so the Willis Tower used to be called the Sears Tower, right? And Pastor Hans' dad or grandpa, I think, helped to build that. So that's kind of a neat thought. But I think Michael, one of our seniors years ago, different Michael, actually got to go out to the Willis Tower to the top floor, and there's a little glass ledge that you can stand on, apparently. You know who ain't standing on glass ledge? This guy. All right, you aren't either. Not standing on glass. I'm like, I'm only 180, and I know it's designed to hold more, but I know how Murphy's Law works. I am not stepping foot on that ledge. Anyway, but for those, you would totally stand on ledge. You would too. You won't jump out of a plane, but you'll stand on glass ledge. Okay, well, you know.
I don't have that much mass.
She very much trusts glass. She could trust she could trust saran wrap. She'd be fine. Anyway, all right, so we're trying to shoot the arrow 443 meters. That's about 180 stories up, okay? It's just insane. All right, so the 443 meters class is the displacement that arrow shooter guy, archer, has to be able to get. But what is working against the archer? Gravity, which accelerates the arrow at negative 9.80 meters per second squared. It's slowing down the arrow. His release velocity is what we would normally call the initial velocity. And that's the question. What velocity would it have to be fired at to get up there? And if it just made it, somebody standing on the glass ledge sees this arrow. Like, what just happened? Where did that come from? And they see this speck down there, this little ant.
Gets impaled.
Who gets impaled. Anyway, or worse yet, it flies up, and it wasn't perfectly vertical, and so when it loops, it lands, and it strikes the glass plate, which shatters, and anyway. I think by that time, it wouldn't have enough velocity to really do anything to the glass. But anyway, that's just my worst case scenario, nightmares type thing. All right, so what's the final velocity, though, when it reaches that top of the Willis Tower? 0. If he just gets it high enough, it'll just stop as it reaches that height. So the question is, what is the initial velocity? What is the firing velocity? Well, what equation do we need that relates to these variables? There we go. Solving for the VI squared, let's just ditch the 2AD as a negative 2AD. But, conveniently, so the negative 2AD. But notice, that's not V sub I. What is that? V sub I squared. So what do I have to do? Take the square root of negative 2AD. And how fast does the arrow have to leave the bow in order to get that high? Ignoring air resistance, of course. We always ignore air resistance.
65.9 meters per second.
That's what I got.
You got 65? Okay, plug it in. You got conflicting. It's okay. 2 times the negative 9. Actually, it's negative 2 times negative 9.8, so the negatives cancel. Times 443. Take the square root. I got 93.18. Let's see, 65 didn't sound fast enough. 93.18, blah, 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 rounds off to 3 sig figs? Yeah, 3 sig figs. 93.2, its velocity, so meters per second. It's got to leave the bow at 93.2 meters per second if it's going to get up that high, which again, I don't know if that's a feasible velocity or not. I should probably look into it, but I'm boring and lazy, so I don't. Questions on this? Second part of the problem says, how long will the ascent take? How long would it take for the arrow to get all the way up there? Again, this is only time up. If we wanted the total time, what would we do? Find time up and then double it, right? But we just want the time that it takes to get up there. Can we do this without using the initial velocity?
Yes.
I don't see a way to do it without the initial velocity. Every equation with t in it has an initial velocity somewhere. Or an average velocity, I suppose. But what can we do for average velocity, class?
Add and divide by 2.
Yeah, basically, since the final 0, we could just cut this in half, I suppose. If you still have the 93.18 on your calculator, cut it in half.
46.6.
So the average velocity is the 46.59 blah, 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 right? But we do want that exact number, not the rounded. So we take this number. We know average velocity is displacement per unit time. Alternate here. Displacement divided by this number. That would work. So may need a memory there. And how much time does it take to get up to the top of the tower?
9.56.
9.508, blah, 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 rounds 9.5 seconds to get up there. All right. The other way we could have done it, because we can solve for time if we use the initial, which we did use the initial velocity, didn't we? We used it to find average. We also could have used the acceleration equation. Alternated, say time is final minus initial over the acceleration. So take negative whatever was on the calculator and divide by negative 9.8, and that would have gotten us the same answer of 9.5 seconds. Questions on that? All right, your homework for this evening is to complete a handout. Homework for this evening, go and complete a handout. And if you're watching on YouTube, of course, the handout is in the description of the video. Don't forget, the exam is coming up in lesson 42. I may have misspoken yesterday saying to you all it was Tuesday. It is Wednesday. Wednesday is lesson 42, and that will be our exam. All right, you are dismissed. Have a wonderful rest of your day.